All right. So let me go ahead and do the following because if I don't do it now, I'll probably forget. Let's go ahead and update these. All right. And we'll let that sit there for the time being. Let's see. No real announcements. Okay. So I just got off the phone with the division chair. Let me make sure this is streaming properly. So this is week 11. I think our last class together is going to be next week on Tuesday. So next week, Wednesday, we'll be done. Exam 3 should open up tonight at midnight. So today we'll finish out section 3.1. Like I finished section 3.1 in my earlier class, so we'll definitely finish that today. We might just go ahead and start section 6.4. That to me that seems like a better use of our time. Just go ahead and finish. Go ahead and knock out 6.4. 6.4 will be the last section. Right now, I have the final exam scheduled to open up on Pearson, but my supervisor also said that we might have a combined final, so I might need to put a pause on our final and see what's going to be the verdict as far as administering the final. But for right now, for this class, basically, 90% of our grade comes from Pearson. I'm going to scale everything as outlined on the syllabus, and then I had to get back to you with the final. But our last class, it looks like it is next Tuesday, and then the following week, I think we're going to have a designated final exam time. So that's the kind of information that we have to discuss as like faculty and come to one accord on that. So I'll be providing updates as far as that. But one thing that does seem to be pretty consistent is like next Tuesday is our last class. So with that being the case, I will go ahead and try to go ahead and finish out these last couple of sections. I am monitoring the chat, so feel free to use the chat if you have questions or inquiries. Right now, you guys can unmute yourself and mute yourself as needed. But I might disable that if I need to like focus and something of that nature. Okay, so again, feel free to use the chat. I am going to go ahead and kind of continue where we left off last time. So again, we don't have that much remaining. We're going to finish out section 3.1 today. Okay, let me move this so I can see. So you can go here. You can go here. You can go like here. You can go here. So for right now, just hold tight. I'll get back to you with more information. It looks like it might be that Wednesday during the final week, but just hold tight, and I have to give you an update as far as the final exam schedule. But it sounds like they do want to do like a common timed, and it sounds like they do want to do a common final. So you just have to hold tight, and I'll give you updates on that. Yeah. Okay.
Thank you.
Yeah, no worries. Let's see. So to continue where we left off with the discussion on exponentials, we want to introduce this notion today with compound interest. This is going to be interest paid on both the principal and the accrued interest. Let's see. I still can't do any assignments on. Alex told me to take the test, but I already did it in the summer. I don't know what did you explain? Did you speak with her on the phone? I would try calling her. Because again, she's gonna know that better than I would. Yeah, I would just give her a call, and I want to say her information should be on the Morehouse website, and like speak to her, like try to find her like office hours and speak to her, because she would know the details there. Yeah, and just do the best you can with Alex. Just do the best you can with it. I'd rather you make sure your Pearson is in order, and we'll figure something out with Alex. Just do the best you can there. But with Pearson, definitely make sure that stuff is in order. And if you're going back over old assignments in Pearson, I would definitely target the old exams. Those should have a heavier weight. I do plan to scale it based on whatever's listed in the syllabus. But I would definitely target the old exams first, just to make sure those are in order. And again, exam 3 should open up tonight at midnight over sections 2.1, 2.2, and 2.3. Okay. So then interest that is compounded annually is paid once a year. So for interest compounded annually, we have this compound interest formula here that you see. So then we have this example. It says when Nita deposited $8,000 or deposits $8,000 in a bank at an interest rate of 6% compounded annually for 5 years, how much is going to be in her account after 5 years? Okay, let's do like this. Get rid of that. Let's get rid of this. Let's see. Okay. So I'm going to use an augmented formula. We're going to talk about this one coming up. So for part A, the future amount is going to be the principal times 1 plus r over n to the power of nt. This is the compound interest formula. So then our future amount, the principal was $8,000 times 1 plus, the rate is 6% as a decimal, so it's 0.06, divided by, let me see, it's compounded annually, so the interest is applied once in a year. Again, 1 times 5 years. Okay. Let me see. So let's do like, let's set it up. The way we had it earlier was pretty good. Just like that. This. You can see here. Okay. Let's see. Hey Siri, what's 8,000 times 1.06 to the power of 5?
The answer is 10,705.80.
705.80 cents. Okay. So then how much interest did she receive? So for part B, we're going to say that number minus the 8,000 is going to leave us 2705. 2705 and 80 cents. I think this is okay. Okay, let's see how do we do. See that one and you see that one, right? So this is the formula that we just used, was the compound interest formula. A is going to be the future amount after t years. P is the principal or the starting amount. R is the interest rate, again expressed as a decimal. Let's see. N is going to be the number of times the interest is compounded in a year, and T is going to be the number of years. So if 100 deposit is a deposit into a bank account that pays 5% annual interest, find the future value after 1 year if the interest is compounded with these several compounders, right? So for the first one, let's say the amount after with 1 compounding per year, that's going to be the principal times 1 plus the rate is 0.05. Compounded in this case is 1 to the power of 1 compounding per year times 1 year, right? So let's do this. Let's go here like this, and let's open this up. Okay. So we're going to do 100 times 1 plus 0.05 divided by 1 to the power of, in this case it's just 1, all right? Actually, let me clear, I'm going to go to my y equals, and let me just type it again. So we do 100 times, the only thing that's changing is the number of compounding, so we can create a formula based on the compounding. 1 plus the rate stays the same, divided by, in this case, we're going to say x to the power of x, okay? Let's quit. And then we're going to call on that function that we just typed in. And so if the interest is, if the compounding, if there's 1 compounding per year, we'll get $105 interest. All right. The amount is going to be $105 after 1 year. Okay. And then 2. So the principal is this, 1 plus 0.05. Now we're doing 2 compoundings in a year, and again, it's going to be the power of 2 times 1. Okay. So now if we apply the interest twice in a year, 105.06. Okay. So then the next one is quarterly. So that's 4 compoundings per year. So 100, 1 plus 0.05 divided by 4, 4 times 1. Monthly is going to be this. So if our compound is, if we do it 12 times in a year, we get 12. Daily will be this many compoundings. One hundred five 13. Okay, so the more compoundings we do in a year, the more return we get, the more interest we earn. Okay. Okay. So we saw several examples where we applied the interest several times throughout the year. So now, what if the interest was applied continuously? Then this is where this is called the continuous compound interest formula. I like to call it PERT, or A equals PERT. A is going to be the amount in the account after T years. P is the starting amount or the principal. R is the annual interest rate expressed as a decimal. Okay. And then T is going to be the number of years. So find the amount when this principal is invested at 7.5%, compounded continuously for 8 years and 3 months, right? So this is going to be A equals PERT, P e to the RT, where E is going to be a function in the calculator, right? So the amount is going to be the principal, which is the 8,300, times E to the power of the rate is 0.075. If it's 8 years and 3 months, 3 months we need to convert to the units of years. So 3 months divided 3 divided by 12 gives us 0.25. So we're going to say 8.25. Okay. And then the rest is just a calculator problem. We get this with it. Okay. So we have this exponential function base e. So like if we look at the graph of y equals 2 to the power of x in blue and y equals 3 to the power of x in green, notice that the base e is very close to 3 to the power of x. All right, so base e is like 2.7 something. Again, it's a function in the calculator. So if we want to use transformations to sketch this graph, say this is our positive y direction, say this is the positive x direction. In general, the graph of an exponential, it starts off close to the x-axis and then it grows like this. Let me kind of redo that. So it starts off close. I want to kind of follow this point. Then it goes like that. So now the transformations here, this is just a general graph of an exponential. If we list out our transformations, this -1 says we go to the right by 1. So we go right 1 unit, and then we go up 2 units. All right. So then all we have to do is take the original graph. We go right 1 and up 2, and that's where we are. And then we still have our horizontal asymptote. Okay. All right. So again, we went right 1 and up 2. So then, say we wanted to create a model for exponential growth or exponential decay. Um, Again, so A of t is going to be the amount after some time t. A naught is going to be the initial amount or starting amount. K is going to be the growth rate if k is positive, and the decay rate if k is negative. And then t is going to be our time. So in the year 2000, the human population of the world was approximately 6 billion people, and the annual rate of growth was about 2.1%. Using the model on the previous slide, estimate the population of the world in the following years. Okay. So if we're going to do growth rate, we're going to say A of t equals A naught times e to the kt. Okay. So the initial amount, so let me see. We want to do, if we let 2000 be year 0 and we want 2030, that means we want to do 30 years later, so A of 30. That's going to be the initial amount in 2000 was 6 billion times e to the rate of growth. 2.1% is a decimal, 0.021. And the time, again, our t was 30. So then that's the rest of all of that just goes into the calculator. Hey, I didn't want anything. I had looking for something earlier. I'm in class right now though. There's no worries. How did everything go? And then with it being the election, so you just kind of have to. Yeah, everybody else was like buying stuff up. Businesses are boarding up because they're kind of anticipating like riots and stuff like that across the country. It's wild. Yeah, I meant to tell you that earlier. I was like, well, she'll be fine. Especially if you're trying to get back before dark. I think it'd be fine. Okay. Well, all right. All right. What we doing? See. Let's see. What are we doing? What are we doing? Okay. Could probably use some juice. Can you get juice in here? Let's get you here. All right. So yeah, let's see. So we're gonna say 6. Now e is linked to natural log. So on the left, I'm gonna hit second natural log. 6 times e to the power of 0.021 times 30 should be 11. Yeah, 11.26, right? So this first one is approximately, put it here, 11.27 billion people. All right? That's based on the model. And then if we want 1990, so that was part A, and then so for part B, again, if we want 1990, then we're going to do 10 years earlier, so we're going to say A of negative 10. That's going to be 6 times E to the power of 0.021 times negative 10. Right? So we can call on what we just typed in and use the exact same thing, but instead of 30, we're going to do negative 10. 4.86, so approximately 4.86 billion people, based on his model. Okay, we're just going to move this way. We're going to go like this. So you see that one there, 10 years earlier, and we see the 4.86. Okay. Then this one kind of shows the answer already. We buy a fishing boat for 22,000. The boat depreciates exponentially. Find the depreciated value of your boat at the end of 5 years. So the exponential decay model, you see it there. The only difference is between this one and the last one, we use a negative exponent because we have exponential decay. And then we just plug stuff in and crunch the number. Okay. Give me a moment. Let me go ahead and load the final section. So this will be the last section for the semester. We're like in the home stretch. You should be excited. Okay, give me a moment. Let me go ahead and load a copy of this. Let me share. I want to send it to Box. Not now. The location here. This one. This one. Are you gonna be acting crazy? Can you stop that? Thank you. Like this. This is week 12. We want to send it there. Send the copy. Not now. Oh my God. Okay. Let me again. Let me go ahead and load the notes for the last section. Matter of fact, I'm gonna stop my stream and